Ah, welcome back. Quick little note I just want to share with all seniors that 2 weeks from today is June 1st. Why does that matter? That's the day your final transcripts get printed. So, you got even less than 2 weeks to finish up all your grades and all your senior projects and presentations. And I just want to make sure that you understand how close you are to the end. And I understand that some of you want to just say, it's over, it's done. But 2 weeks, you can make it 2 more weeks. You do not want to throw anything away because you're done and you say, I'm not going to do work for 2 weeks. You do not do work for 4 years, 7 years, or however many years you've been at BL just to say, nah, 2 weeks, I'm done. I'm throwing it all away. So, what we are going to do today is that last week we started the introduction to energy, and it seems like, for the most part, we feel pretty comfortable with this, whether the equations are simple or you remember them from last year, whatever it is, it seemed to go well, which is good. I like that. I'm thrilled to hear that. I'm thrilled to see that. So we're going to get into some roller coaster stuff. I don't know how many people looked at the extra links, the skate park link and the roller coaster link that I added on last week's assignment. They weren't required, so I imagine probably not a lot of people check them out. But if you are confused about what we're going to do today, those are good resources. I would check those out as a way of trying to understand this concept. The concept that we're going to get into today is the law of conservation of energy. This is the most fundamental law in all science, not just physics, science. This is true everywhere and every time. And I know I've said it before. Energy cannot be created or destroyed, only transferred among types of energy. So I said that the only thing that you eat is sunlight. And I don't want to get too much into this, but sunlight provides the energy for every piece of food that you eat. Now, here's my question, and I don't get tripped up on this. You do not get energy from drinking water. Sunlight does not contribute to water. The human body needs things other than energy. Okay? The human body needs the raw materials to build the body. The human body needs water, just so for other reasons. You took biology, I don't want to get into all that now, but the human body needs other things. But anything that gives your body energy ultimately comes from sunlight. Sugar, carbohydrates, foods. So like, you eat some, I don't know, use some Cheetos, hot Cheetos. I mean, granted, the chemicals that make the hot are terrible, and your body will just expel those. But the Cheeto itself is made from corn. I don't know if you guys knew that or not, but the Cheeto itself is made from corn, and corn gets its energy from the sun. Awesome. You eat a burger. Beef, cows, grass, sun. Always goes back to the sun. Oh, fish to plankton, plankton to sun. Okay? You can't escape it. That is a form of conservation of energy. So the sun is constantly pumping energy out. Where does the sun get its energy? It gets it from the nuclear reactions that happen in the sun's core. So wait a minute. Bizzuto, if you're saying that energy is conserved, there's only so much energy, the sun cannot give energy out forever. Eventually, it would run out, because if it gave it forever, that means there would be an endless supply of energy. And you're right. Eventually, the sun will run out of energy. And that's when it goes nova. Supernova. Exactly. Conservation of energy at the astronomical level. We talked primarily about the two types of energy, potential energy or kinetic energy. We're going to talk about those today in the video, but I'm going to have you do some Khan Academy to introduce another type of energy. It's called spring energy. Or, yeah, Hooke's law of spring energy. It's just another type of energy. It's the energy that an object has when it's in a, that's not how you spell spring, when it's in a spring, or anything elastic. So like, you can consider a trampoline to have spring energy because it wants to go back to its original position. When you fire a little toy dart gun, it's got some spring energy because when you you pull it back. So you pull the spring wants to go back to its original position, and that's energy. Your car technically has spring energy. That's what your shocks are. Your car is actually on springs, not just like slinky springs, really, really intense springs. So if you ever get like a shock or alignment repairs and stuff, they can kind of be expensive because the springs have to be just a certain way. But just so you know, energy is energy. So whether you're talking, and Khan is going to refer to PE as GPE, gravitational potential energy. I don't want you to get mixed up by that. It's just there's going to be more types of potential energy. When it says GPE, it means the potential energy that comes from gravity. That's the one that we really care about. KE is going to stay the same. But it doesn't matter. It doesn't matter how many different types of energy that you have. They all follow the same rules. They get conserved. Obviously, there are dozens and dozens of types of energy. We're not going to be able to get into them all now this year. But we're going to focus primarily on these two in this video today. But the spring energy, you'll learn, and I'll let Khan teach you spring energy. It's really easy. If you just think about it, guys, springs want to be at a certain length. So if you stretch out a spring and you let it go, it's going to go back to its original position. It's the whole point of a spring. It wants to be in its original position. So you can give it energy to stretch it, and then when it goes back, it's releasing that energy. You jump on a trampoline. Why do you get thrown up? Because the spring aspect of the trampoline wants to return to its starting position. Okay, there. I just taught you spring energy. I didn't give you the equations. Spring energy is 1/2 kx squared, but I will let Khan explain that. Oh, okay. What the heck is this? You have a ball rolling down a hill. All right. This is the same ball at 4 different points in time. Okay, so this isn't a different object. It's the same object rolling down at 4 points in time. I want you, and we did this last year, so you might remember this, you may not, I don't know. You have to solve for the bottom stuff first. You have to solve for the mass and the total energy first before you can do anything else. Because these are the things down here that remain constant. Hopefully you recognize that as the ball rolls down the hill, the potential energy will decrease. And as the potential energy decreases, it's got to be going to another form of energy. It's going to be going to kinetic energy. So let's just look at what we have. So, okay, the potential energy is decreasing. So we can already assume that these PEs are going to be less than 900. And that means if the KE here is 490, we can assume that these KEs are going to be more than 490. And, excuse me, less. These KEs are going to be less than 490. And this KE is going to be more than 490 because as it goes down the hill, the kinetic energy will increase. So as the potential energy increases, as the potential energy decreases, the kinetic energy increases. Tell you what, let's look at numbers. I misspoke, and I apologize about that, but hopefully the numbers will clear it up. All right, we got to get the mass. We have our two equations. We have PE equals mgh. We have KE equals 1/2 mv squared. All right, so this is what we got. Let's solve for the mass first. If we want to solve for the mass, we need a spot that has either a PE or an H, or a KE and a V. Oh, look at, we need 2 pieces of information. So it's definitely not spot 1 and spot 4. It's either spot 2 or spot 3. Spot 3 has a KE and an H, but KE and H are not in the same equation. They don't go together. Spot 2 has a PE and an H. They go together. So we can go ahead and do this. So 900 equals M 9.8 5. And when I solve that out, I get a mass of 18, I'm going to round, 0.37. I'm going to get a mass of 18.37. Now that I know the mass, it's actually going to be fairly easy. Let's look at spot 3 now. With spot 3, I know the kinetic energy, and I know the height. With the height, I can go ahead and solve for the potential energy now that I know the mass. Because I know the mass, I can just go ahead and do 18.37 times 9.8 times 4.2. And if I'm type all that into the calculator, all right, let me actually type that into the calculator. I'm going to get a potential energy of 756.11 joules. Awesome. I rounded again. Now to get the total energy, now that I have the PE and the KE in the same spot, I can add them and get the total energy. I want to just go ahead and throw that out. You need to add the PE and KE at the same spot. So what some people would do is like, oh, Pizzuto, to get the total energy, could I just add the PE here to the KE here? And the answer is no. You cannot add them at different points in time. You have to add it from the same point in time. So if you added those two, that would give you nothing. That would not give you a useful piece of information. So please do not fall into that mistake. You have to get the PE and the KE at the same point in time. So our TE is 1246.11. All right, cool. 1246.11. This is easy now. I know every spot has to add up to 1246.11 because as the ball rolls down the hill, it's transferring its potential energy to kinetic energy. What do I mean by that? Well, let's go ahead. 1246.11 minus 1100. This is easy. Let's go ahead and think about it. 146.11. All right. 1246.11 minus 900. 346.11. Let's look at this last spot. This last spot, all I have is the velocity. So I can use the kinetic equation of 1/2 mv squared because I know the mass is 18.37, take half of that, times velocity squared, which is 10 squared, and I can get the KE to be 918.5. I can then subtract it from the 1246, and I can get the PE is 327.61. So let's just examine the potential kinetic energies. I know we have other blanks. Yes, I know. We'll just hang tight. We'll get there. But let's just examine it. As the ball rolls down the hill, the PEs are getting smaller. And that makes sense because it's getting closer to the ground. As you roll down the hill, the potential energy is getting smaller because the height is decreasing. As you roll down the hill, the KEs are getting bigger. Well, that makes sense because as you roll down the hill, you're getting faster. Those are the quantities that connect to those. So you can use these PEs and KEs to solve for the missing heights and velocities. And they need to logically fit and make logical sense. So we know that if this PE is the highest up here, we know this is going to be the highest height. If we know that this KE is the highest here, this is the highest velocity. So I know that all these other velocities are going to be less than 10. They have to be. Let's not lose sight of the concept here. You are losing height and gaining velocity as you roll down the hill. You are losing potential energy and gaining kinetic energy. The energy isn't disappearing, it's transferring between the two types. I'm not going to solve for all those blanks because that's just like the assignment that you did before, and you don't need to see that again. Okay, what about this? Let's just say this box is falling down, all right? What are we going to do? The first thing we need to do is get the mass. All right, how do we get the mass? 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 Don't know. Oh, I do know. I need a spot that has either a PE and an H or a KE and a V. Because Those are my only two equations. So we got four spots again. It's the same object at 4 different points in time. It cannot be spot 1 or spot 4 because there's only have one piece of information. It's either spot 2 or spot 3. This time it's going to be spot 3 because KE doesn't relate to H. They're not in the same equation, so I can't use them. KE relates to velocity, so I can use 5,250 equals 1/2 m10 squared. 10 squared is 100, half 100 is 50. And I believe when I divide by 50, it's going to be 105. I should type in that better. I think I'm right though. I am, yes. 105 kilograms is the mass of this crate, this box that's falling down. Once you know that, now let's go ahead and look here. We used these. Is there anything else we could solve for spot 3? Not yet. So let's look at spot 2. If I have the kinetic energy, I can use the height to get the potential. Oh, nice. PE equals mgh, or 105 times 9.8 times 9. So the potential energy is 9,261 joules. That's the potential energy. I did PE equals mgh. We have to know these equations. We're just going to keep using them again and again. This is the K equals 1/2 mv squared. We're just going to see those two equations again and again and again. So that's why the assignment last week was just to make you feel comfortable with them and how to get a total energy. But you should even remember from last week, if you have the kinetic energy and a height, you can turn the height into potential and add it to get the total. So the 9,261 plus 1,500, so the total energy is actually 10,761 joules. And all those trends are going to fit in. And everything can fill in nicely from there. So you could go ahead and use the kinetic energy to solve for the velocity. You can go ahead and subtract from your total energy the 10761 minus 5250. So I know that the potential energy here is 5511. I can do the 10,0761 minus 9,000. I can get 176. All right. And then I can use the height to get the PE, subtract to get the KE, KE to get the velocity. I'm not going to do all that intermediate algebra because you know how to do that. This was the tricky part right here. So, quick review. In order to find the mass, you need to find a spot that has both this or this. You need either the PE and the H, because then you can use the PE equals mgh. You'd only have one variable. You always know gravity. You'd have the height and you have the PE, so you can then solve for your unknown. If you have to find the mass, you can also use KE and V. Because if I look at these, right, if I know this and this is my only unknown. Once you get the mass, now always get the mass first. Whenever you're looking for these problems, you need to get the mass first. But once you get the mass, then you can get the total energy. And once you have the mass, you need to find a spot that has either a PE and a KE, a PE and a V, because you can turn the V into KE, and add them up to get the TE. Because remember, the last time I said that TE equals PE plus KE. So don't lose sight of the concepts. And then eventually we're going to add more energies. We're just going to add more plus signs here. We'll do plus spring energy, but that's coming. That's coming later this week. A height can be turned into a potential energy. So if you have a height and a KE, you can add those up. And then if you just have a height and a velocity, you turn that into potential, that into kinetic, and you can add them up. So it's a puzzle. You cannot do these problems in order. You have to jump around and think conceptually about what you know. And that's it. Yes, we're going to have a test, like a Google Forms test on some momentum and energy next week as our last assignment of the year. The Chromebooks will be locked for that assessment, but I will talk more about that on Wednesday. I just want to make sure that you understand that that's coming. And then today, we're really going to focus on the concept of conservation of energy. Good luck, and if you need help, I am here. I will see you guys next time.